Now there, is my audio on? Oh, my audio is on. I don't hear myself yet though. Is on. I don't hear myself yet though. Okay, since I had trouble getting into Blackboard, I am going to pick this up this way and go in here and do the word of the day this way. Now you'll have to go into Blackboard because you probably can get in, but I'll resolve all this afternoon. Hopefully, if I don't, then let's see, what's a good word? Black bear. How about that? All one word. All with no space in it. All right. Oh, I shouldn't have done that early. So this is, oh shoot. So, but if you come into the stream, you pick it up at the beginning. So this is 4 minutes before class starts, but sorry about that. I should not have done that way. So, what I'll do is I'll just sort of wait here for a minute. Back to the curved gates. Okay. So I'll wait a couple minutes and we'll start. Let me check the filter here. So let's head off into here. So what I'm going to do today is talk about curve gates. And curve gates are very, very interesting. Let's just look at it from just from observation here without reading too much of the words. He starts talking about the horizontal component, and somewhere he talks about the vertical component. Now, if you get down in here, he starts talking about a curved gate that looks kind of like that. So let me take two cases here. And this one doesn't look like a circle to me, so I'm going to draw my own over here. And let's, but I'm going to mimic his. Let's see. His looked very much like that. So you come down a certain height. And then from here, I don't think, maybe I can. So here, I can get rid of this in a second. Here, I'll make it red. And I'll come back off over here. And then I'll say, my gate looks like that. And I think, yeah. So here's my gate. Now he stops at that, right? Now he makes it come on back, but I'm going to do it a little bit different. I'm going to call this the hinge, and maybe I'll do this too. I'll say the water level is back here. There's a concrete wall here. There's a hinge here. And then I'm going to say there's some type of support mechanism here, so that it's possible that somehow there has to be a force here that, if it's not correctly done, will break this concrete off. So how do you find the load on this gate? One is to have a interesting imagination. So let's imagine that we have that, and what we're going to do is we're going to subdivide this into two portions here. So suddenly I go out here and I essentially freeze this block, or have a neutrally buoyant item, which is a kind of a solid here. If it's neutrally buoyant, then the gamma is 62.4. In other words, if this is H2O, and I'm assuming this is about 62.4, if I put a brick or a block in water that has a gamma of 60, then it floats, and part of it will sit out of the water and the other part will sit in the water, and it'll be partially buoyant. If I put a block that is 63, then what it'll do is it will just slowly sink until it hits the bottom of the water. And so it sits there because the ground needs to push back up on it a little bit because it's too heavy for water. And we'll look at all this later. But we're going to assume that this is neutrally buoyant. In other words, the weight of this block is equal to the volume of the block times the gamma of water that it sits upon. Anyway, so we have another one. Yeah, I'm going to try my best. So it is a quarter of a cylinder. Its centroid is slightly shifted to the left, and it weighs something as well. And what its weight is, the weight is the gamma of the water and the volume of the quarter cylinder. Now, These are two independent objects, the blue and the red. So now what I'm going to do is I'm going to do something interesting. I'm going to copy it with all of its splendor, because then I want to do something to it. And I'll move it to the right. Oh, wait, I thought I did a copy. Copy, then a paste. Okay, here we go. Copying this ugly drawing I just did. And the reason I'm copying the ugly drawing is because I am about to turn it into a free body diagram, meaning I'm going to try to get rid of all this. This is still the case. And now these two objects, the yellow object and the blue object, I've taken off the concrete. So here's what happens. I've got a force pushing of the water, pushing this to the right, but I have the concrete over here, offsetting it up into the hinge. So concrete has been removed, and this is the force from the concrete on the water. Or let me say it, on the yellow object. This is the force from the water on the yellow object. And guess what? They exactly cancel each other out. Now, when you get down to the blue, you got something different. And what you have there is you have a continuation. I don't know what it's doing. I don't know why it does this. Here, let's try to see if I can lasso. Alright, then I can go back. Oh no. Now I can only lasso. Okay. Oh jeez. Oh, okay. I got it. I got it. Okay. Can I select the color? Yes. So now, I'm looking at this. And what I'll do is, since the X force is offset from the concrete on both sides, it has nothing to do with the gate itself. So now here's my free body diagram. I do have a hinge force here, but let's start putting numbers with it. Let's say this is maybe 10 foot deep. And so maybe this is a radius of maybe 3 foot. And now what is the force if you've got that? And you have water, of course. So what do you have here? Well, I got two sets of forces. There's two ways I can do this. The one way is using the delta is equal to I bar XX over Y bar area, and then F on the gate is equal to gamma H bar A. Now, what is the gate? Now this is, I'm going to do it this way first. Now, what is the gate here? Okay, so now it is a curved gate, but we're only talking about the force in this direction. Meaning, if you were sitting back here, way back here, and you looked at this what you would see, and what we'll do is we'll make the thing 1 foot into the page. What this guy would see would be a gate that, let me do the aspect ratio at least reasonable. He would see it from here to here would be 3 foot, and then it would be 1 foot into the page. So again, okay, so here's your guy. I'm gonna try my best to do this. He sees this. Here's his hinge. And he's looking in here and he sees this. Here's your hinge connected to some bearings maybe. And it turns out it is approximately a radius of 3. And so he sees this from a perspective. But this person's far enough back that what he sees is this. He sees a gate. He sees this area. That area is 3 high and 1 into the page. So now, when he sees this, he recognizes that the horizontal force on this gate, the force going that way, not the vertical, but the horizontal, or I could say the x component, is equal to gamma h bar a. Well, the a he sees is 3 by 1. He sees h bar. What is the distance down to the centroid of this gate? Now he's underwater, and what he sees is this. But his head is such that he sees that this is 10 foot to the top of the water. So if you look at the centroid here, this is 1.5 feet below it. So his h bar from the top of the water to the centroid, what he's seeing. Now this is just to find out the horizontal force, not its location, is 11.5. And of course it's 62.4. So if you multiply that out, .4 times 11.5 times 3 foot, 2152. 2152.8. So that's the force total on that gate. The fact that it's underwater and the fact that this location is deeper than that location indicates that the force or the pressure down here is higher. Therefore, the location of the load is under it. How far? That's a term I like to call delta. And that is I bar xx, y bar area. Now, that is 1/12, the base of 1, the height of 3, the third, over y bar. Okay, in this particular case, y bar and h bar, let's think about what this is. An inclined gate is the top of your water. Here might be your centroid. This would be h bar. This would be y bar. However, if this angle becomes 90 degrees, let's take a case in point where, say, it's almost 90 degrees. So here's your centroid. The distance from this is y bar, and the h bar, when they coincide, when they basically become 90 degrees, when it becomes a vertical gate, which is what we're saying, h bar is equal to y bar. So you get 11.5, which was h bar, and area is still 3. So what you get is Let's see if I can get, yeah, it's all on the screen. Okay. 3 to the third divided by 12 divided by 11.5 divided by 3. 0.065, 0.065, 217. So now what does that mean? Okay, from a free body diagram perspective, what that means is this. It means I can take this picture again and copy it. Put it over here somewhere. However, when I'm in here, I can take this force off completely, and I can replace it with a force that is going so, and it's 2,152.8, and it was pounds, and its distance is, the centroid's here, and it's 1.5 down to here, but this delta is 0.06517. Now, let's go up and calculate these other two forces, because really what I've got is I've got only a few forces to deal with. This one, this one, this one, this one, and then the hinge force. What I'm going to do now, do something interesting. Copy this thing yet again. Move off to the right again, paste it. This time, I'm going to make them close enough so I can see them both on a similar part of the page. This time, I'm going to go ahead here and remove the bottom concrete, because this is the force that's being applied to it. I'll just call it F. Oh. I'll just call it F. Now, what I'll do is I'll go ahead and take the yellow off, and I can move this. And I'm going to do this, and then I'm going to say I've got a hinge force in the X, and a hinge force in the Y, and since this is 3 feet right here, the distance from here to here is 1.5. Now this distance is 4r over 3 pi. Now where did I get that from? Give me a second here. Well, I may have to zoom out so I can see if I can find them here. Okay, we had a hole, there we go. So, this is the centroid of that location. So if you had a homogeneous body that was like this, and it had a certain weight, its weight would be located at the centroid, 4r over 3 pi. So here's your 4r over 3 pi. Now, I have 2 other pieces of information. One is the weight of this one, which is 62.4 pounds per cubic foot, times the volume of that, pi r squared, but r is 3, over 4. Why over 4? Because you don't have 3 of those. It's only a quarter circle. That's the volume. Times 1, because it's 1 into the board, and that gives you the weight right there. 62.4 times pi times 3 squared divided by 4 gives you 441 pounds. I'll just drop so that's the weight of that. The weight here was, okay, it was 10 tall. Oops. So the object there was 10 tall. It was 3 wide because it sat right on top of this, and this is the radius. This distance right here is the radius. So it's 10 by 3 by 1 in the board times 62.4. So that's 30 times 62.4. 30 times 62.4, 1,872 pounds. Now with this drawing, the next thing you need to do is go in here and now sum the moments about the hinge. And you can do it any way you want. You got this force. You got this force. You got this force. You got that force. But you also have the hinge forces, but they don't produce a moment about themselves. So let's just take off and start with the F. Now the F is spinning around this way. So it's a minus F. The moment arm is 3. So we took care of this one. Now let's take care of this one. Now it's going in the positive direction. And I'm going to list it down here. So it's 2152.8. And its moment arm is the 1.5 and this put together. So it's a 1.565,217. So all I did is I just added 1.5 to this. The 6 doesn't have any, the 5 occupies that. So it's a pretty easy addition to do right there. Now I've got this one. Okay, this one's producing a moment this way, which is a positive, which is 441. But its moment arm, okay, it's 441, but its moment arm is this distance, which is R, minus that distance, because here's the moment arm. So here's the distance, which is the moment arm. So you take R minus 4R over 3 pi. And R minus 4R over 3 pi. Well, R is just 3. So you get that. Next thing, you've got this one, which is quite a load up here. And it's 1.5 from there. But it's spinning in this direction. Okay? And that is a positive. And it is 1,872 pounds times a moment arm of 1.5. And that is all you've got. Now, if you want to find the answer, you of course move all those to the other side and you get 2152.8 times 1.56, 5217 plus 441 times 3 minus 4/3, or 4 times 3 times that, then plus 1872 times 1.5, and all that divided by that 3. So I can figure it out real quick. Here, I'll try my best to do it. So 441 times 3 minus 12 divided by 3 divided by pi plus 1872 times 1.5 and divide all of it by 3, and I got a problem. And I think my problem is I thought I put a parentheses right there, but I guess I didn't. So 23 and 13 roughly. Now let's do something interesting here and see if we can keep what I'll do. Well, let me paraphrase what I did. So what I did initially is I started by finding the vertical force, which was this and this, and we found the horizontal force, which was this one applied over here. We added them up, we put them on the object, which was the blue, and we took it across and broke the distributed load down further to a point load and found its location and went through this process. But I'm going to take a stop here and I'm going to show you something interesting that occurs here. And this is a pretty good case in point. Let's say, since all the numbers are listed here, I'm going to take this. I'm going to do a copy. Uh-oh, I was supposed to do a copy, but I think I hit the X instead. And now I'm going to drop down here maybe and put it right there. And I'm going to zoom in on it. This time, I'm going to ask a simple question. And that question relates to not this force and not these forces, but let's assume for a moment that this thing is being supported. I'm not sure how to draw this, but I'll try my best. It has struts that go across to a center spot right here. And so it's holding this. So this is being held right here in a pin. And then I'm going to want to know, what is the moment about that new hinge? Okay, let me take those off. And say, now my spot I'm interested in is the hinge here, which in other words, the gate can open or close by rotating. So maybe later it might rotate to right here. But for the moment, I want to know the moment about that hinge. So now my distances become a little bit different. So let's start summing the moments about the hinge here equaling to 0 equals to it's, you know, in other words, do I have to supply a twist in order to keep this thing sitting, or will it naturally drop? Now we got to assume the green gate weighs nothing. And so what we'll do is sum the moments here. So we'll start with this one. We'll say 2152.8 times, and if it's going this way, I guess I'll make that positive, times 1.565217. Now, this one's creating a force the other way, so it is minus 441. Now here's where I will probably wish that I did not drop my digits. So that's the moment arm. And the next one is 1872. Now, it is doing the same thing. It is producing a moment this way, which is opposite to positive. So it's supposed to be a negative, times 1.5. Now, was there extra digits up here? I don't know. So let's look at each one of these. Let's look at this one first. Now, 2152.8 times 1.565217, 3369.6. Now, let's look at this one. Well, yeah, let's do them individually. 441 times, let's see, the 3R is going to be, it's going to end up with being 4 divided by pi. 561.50 minus 1872 times 1.5, 2808. Now, I need to also put in the torque that I might need to be required to do, the torque. So let's say I put in this torque. So in other words, I really need to put in that torque as well. So let's add these two numbers and see approximately what we get. Plus 561.5, and I get 339 point, okay, hang on, 3369.5. Now, technically, if I would have carried all my digits, those would have exactly equaled. And so there is no torque required to have a spillway like that, or to have a curved gate like that. And why is that? And the reason being is this. If I go out and I look at a gate and do my reasonable best up to, so here's my curved gate, and then I notice I want to know about the center here. Well, if this is full of water, say this is air and this is water, something interesting happens. And we talked about this earlier. If you have an area and you have a pressure here, your force is dictated by, say you have a high pressure here, your force direction is dictated by the orientation of that area. In other words, if I did this and the pressure high was here, then essentially its direction, the force direction, would be oriented normal to the area. With that in mind, what does the pressure profile look like here? Well, what it kind of looks like is, first of all, when you get down to here, you already have a pressure. And when you get to here, you have a higher pressure. And so the distribution kind of looks like this, or maybe it looks a little bit more like this. Deeper, higher pressure. But the key is, so if you take a tangent here, it's always 90 degrees. And all this force distribution, or the pressure distribution, they all pass right through this point, meaning that any little depressure here, any little strip of pressure, produces no moment about that hinge. This is why if you go to Lake Darnell, I don't know if I have any pictures there. I might be able to get some. Let's see. If I can go to if I go here, come on, come on, come on, come on. I believe the spillway's right here. Let's see if I can. Sometimes, apparently not this time. Okay. No pictures here. That's okay. I don't know what's going on. Let's see. Is there any way to get a picture? Somebody had to have taken a picture here. Anyway, if you get up here to the spillway, I don't know if you can see this. We can kind of see it a little bit. These gates are all curved. So they are all curved like this, and the water fits underneath. The other place I might be able to get, I bet you I know where I can get a picture of this. Let's see. Because there is, okay. Okay, so if you go down here, why do I have arrows here? Okay, let's see if I can see a picture here. That's on the back side. I don't know that that was the picture I wanted. It jumped to the wrong one. Anyway, if you zoom in on these things, if I can zoom in, you'll notice this is not working out very well. All the gates are curved. So essentially what's happening on all of these is there's a good justification for having a curved gate. So they're at Toadsuck Park as well as at the Darnell Spillway. You have a gate which it might be elevated, but it's still, and it might go past the corner. In other words, it might be larger than, but what happens is it's supported here in the center. So these are those rods that you saw, and the water might be here. And then there might be some sort of concrete under this. And then the water can kind of shoot out the bottom depending on whether you open it or close it a little bit. The key is to open it, you just have to torque it a little bit and hold its own weight. The pressure of the water doesn't make this torque, opening torque, any larger based upon the water, whether the water is this deep or this deep, unless they didn't manufacture it as a circle. Because if the water is that deep, for example, what you're going to have is a pressure profile comes down, increases linearly. So here's your water level. But all of the pressures exactly go through the center. So they all go right through this hinge. So if the gate weighed nothing, the torque to open it would be 0, but the gate is going to probably weigh something. So this whole thing going to weigh something, it's probably going to weigh quite a bit. So all you got to do is overcome that. You could, I mean, I don't think this is what they do, but you could actually weld a big long rod there and put a weight over it, and then your center of gravity would move over. If you move this weight to the right, it opens the gate, and if you move it back, it when I say open, it opens that way. When you push it back, it sort of goes back down. So you could actually have an offsetting weight. Don't know if that's what they have, but somebody might, one of you guys might know more than I do. So so the question is now, what happens to a curved gate that goes in the other direction? And I got probably just enough time to do it. In other words, the gate comes down, right? And before we had that. Now we're going to have this. So we've got a gate here, right? But this time we have water on the back side. So this is a little bit different than the state park, because the state park is such that the gate sits there and it doesn't have an elevation that's above it. But you could have this same situation where you had this, and you want to know what are the forces on this hinge. I guess what we'll do is we'll deal with that next time, because I just noticed it's 12:42, and I guess on Friday what I'll do is I will try my best to get to class, I think, into the actual classroom, because actually I think I should be able to connect up to the Wi-Fi at that point. But essentially we're done with chapter 2. You've got homework on it, and I'll come back and work one or two of the curved gate problems in here. And there's not a lot of curved gates in here. In fact, I don't see. There's one, and there's another. I mean, there's another. We'll work that one, because that's probably a good one. And then we'll look at this one. Maybe we'll do this problem. So you know what? I'll just identify the ones. So yeah, I think I'll do this one as well. So I'll do all the ones in red. I don't know if I can complete all those on Friday, but we'll see what we can do. So I think for the most part, we may. Well, let me lead us on to what we're going to do next, and that is Bernoulli's equation. And you know what? I might as well just slip this in right off. Okay. So he goes through a derivation here. A lot of equations. And then he ends up with this equation, which actually becomes this equation. He says this is constant along a streamline. Well, what is a streamline? And what are we talking about here? And let's just fill this in, because then I save a little bit. So what does his equation look like? It has P, pressure, plus 1/2 rho V squared plus, and he has a Z and a gamma here. He has a gamma and a Z. Now along a streamline, gamma Z equals to a constant along a streamline. What does this mean? First of all, what is a streamline? Let's say you had a particle here, and you had it going through this path, and so it ended up here. So if you had particle 1, and say later you found that the same particle ended up down here, if you were back in dynamics, you would do 1/2 mv squared plus mgh, and this would be state 1, and this would be state 2, particle A, and particle A, it's still the same A. So you'd say this equals to 1/2 mv2 plus mgh2. Now what is this saying here when you're doing this? What you're saying is it's just constant along the path, or you could say the streamline. So the streamline kind of indicates that you may have several particles stacking up doing this. So it might not be particle A, particle B might be right behind it. So particle B will come through this point, particle C will come through this point. So it's kind of a stacking here. So how does this look like that? Well, it looks quite a bit the same. So we'll address the pressure in a minute. But let's say, what is rho? Rho is the mass per unit volume. And this is V squared. So wait a minute. That is actually this per unit volume. So let's take a look at that. Let's sort of say per unit volume of whatever particle that is, per unit volume. Well, now let's look at this and compare H to Z. They're actually the same thing. In the H here, you would have figured out I would have climbed a certain distance. Well, what they do here is they say, well, we're going to call this Z. So what is mg? That's the weight per unit volume. That's actually gamma. So in fact, this is the potential energy per unit volume. This is the kinetic energy per unit volume. What is the P? P is an interesting thing. So let's imagine you've got we'll just do it like you're in a pipe here. So you're running down a pipe and you have a pressure difference here. And in this little thing, let's see. So in the energy equations, you had something called F times the distance. So if you pushed a block with F and it moved in the same direction, it basically became the work added. So in other words, you might have F dot D plus 1/2 mv squared plus mgh, right? So you had this extra term. Well, if this is an area, then I would say that the pressure here, the force on this area, the pressure is going to be force per unit area. But what distance is it moving? Well, it might move a certain distance d here. So if you had the force and you said, hey, wait a minute, the force is going to be the pressure, pounds per square inch, times the area in inches squared. I don't have to use inches, but that'll be your force, times what distance did it move? It moved a certain distance here. Now, if you look at this thing and you say, hey, wait a minute, I got a certain volume here. The volume is A times D. So it sounds weird, but F dot D per unit volume. Okay, remember, to get the Bernoulli's equation, we took the energy equation and divided by the volume. Well, F dotted with D would be P area dotted with your D that you moved. The volume would be the area times the D, and you get back P. Sounds really weird, but this is the force applied per unit volume. Sounds really weird, but in essence, there is almost no difference between this divide all that volume you get the same equation as P plus 1/2 rho V squared plus gamma Z, where this term yielded that one, this term yielded that one, and this term yielded that one. So essentially it's, now there could, in dynamics there were other forces that you could do besides pressure, but in fluids this is all you got. So this is simply saying constant along a streamline. Now, we're exactly at the end of class, so I'll end it here, but I think at this point, this explains enough about Bernoulli's equation that what we'll do next time is we'll come in and work some statics problem, fluid statics problems, but then we'll be able to roll in on Monday and start working Bernoulli's equation problems. And so I'll go ahead and figure out how to stop the stream.